So in our previous sessions, we have started with programmable logic device, and we have also seen what is your ASIC design flow, FPGA design flow, and what was before your FPGAs, like the programmable logic devices we have seen, and we have seen PLAs, PROMs, and how this programmability is achieved, like what type of technology they use it to, right? So this basic things we have covered, and let us try to understand in this particular session, like what is actually which is present inside an FPGA, right? So basically, FPGA stands for Field Programmable Gate Array, right? This we already know, and this particular FPGA is not a single chip doing one job. Okay, so basically, we have internally a reconfigurable digital system, which is made up of something known as configuration logic blocks or logic elements. Okay, so in some FPGA architectures, you might see this term which is known as CLB, configuration logic block. And in some another FPGA configuration, you might also see this configuration which is known as logical elements. Okay, but the functionality is same, whatever they are doing that is same, but the name and notations are different, that's it. Okay, so inside your FPGA you're going to have something known as CLBs, or you can also say them as logic elements, both are same. And you will have something known as programmable interconnects, which are used for routing, and input output blocks, and configuration memory, embedded hard blocks. Okay, you can also say them as BRAMs, block RAMs. Okay, we will see what do you mean by this, right? So we have block RAMs, DSP blocks, locking resources, and everything will be arranged in 2D architecture. Okay, so these are the things which are present in an FPGA, which make them reconfigurable, right? Now, so let us see first of all the internal architecture of this FPGA. Yeah, I was talking about this particular thing. So your FPGA is going to look like this. The internally we are going to have something known as CLBs, which stands for configuration logic block. So these are like your islands where it is surrounded by this routing lines. Okay, so these are all our CLBs. So these are all our CLBs, and the CLBs will be connected with each other using this routing patterns, which we can see, right? So this is nothing but my interconnects. These interconnects are used to connect my CLBs. Okay. So using this CLBs and interconnects, we can implement whatever the functionalities we want to implement. We can implement them. We can implement each every logic, or whatever the logic we want to implement. That logic we are going to implement, but how we are going to implement that particular logic, how the CLB is going to achieve whatever logic we wanted to, that we are going to discuss, right? Now, for example, if our FPGA wants to act as a UART controller, which is going to control a UART frame for filtering or for removing any packets, right? So that particular logic it can implement. Like, let's say, suppose if it needs to act as a counter for counting the number of clock pulses, it can act. Like, let's say, suppose if it needs to act as a finite state machine, which is going to just act as a simple traffic light controller, or if you want to have a some, let's say, vending machine or something, right? So it can act. Okay, so how that particular configurability is achieved by this FPGA is nothing but using this configuration logic blocks. Okay, and this will be connected using this interconnects. Okay, now let us before going to what is actually which is present inside this CLBs, we need to understand a little concept. So let us say, again, I'm going to take a simple example. Let's say if I'm going to have a OR gate. Okay, I will take a very simple example, which is an OR gate, A and B. Okay, and this is my output Y, and I'm going to have inputs A and B, and Y output 0, 0, 0, 1, 1, 0, and 1, 1. Can anyone tell me, can anyone fill this particular table? It's a very simple question. What will be my outputs in the chat box? I'm waiting for your responses. It's a very simple question. 0, 1, 0, 1. Yeah. Okay. So it's a simple OR gate, and simply it is 0, 1. Am I right? So that is nothing but my truth table which I'm drawing, right? So I'm going to write down 0, 1. Someone has unmuted their mic. Yeah, please mute yourself. Thank you. Yeah. So it's a simple OR gate. Okay. Now let's say if I want to implement this OR gate on an FPGA. Okay. Let us not try to go in deep like what is going to happen. I'm going to give you a just brief idea of how things are going to work, right? Now, let's say in my FPGA, I have something known as lookup table, which is known as LUT, which stands for lookup table. Okay. Now, what is this lookup table? What it is going to do? Let us try to understand. Before that, let's try to have a simple memory. Okay. Let's say this memory is going to have a width of only 1 bit. Okay. And it is going to have total 4 number of locations. Okay. Let's say this is location number 1, 2, 3, and 4. This is index 0, 1, 2, 3. Okay. Now, for accessing my 4 locations, what do you think the number of address bits I need to have? For accessing 4 number of locations, what do you think the number of address bits? What should be the width of your address to access 4 number of locations? Is my question. Can anyone answer this? For accessing 4 number of locations, how many bit address do I need? I need responses from each and everyone. Let's keep the session interactive so that you will not feel bored. Only 2 responses? Just give it a try. It may be a correct answer, it may be a wrong answer, no issue. No one is going to judge you. Exactly. So we need 2 bits for we need the address as 2 bits for representing 4 number of locations, right? So if you're going to take for representing 0, you need 2 bits 0 0. For representing 1, you need 2 bits 0 1, 1 0, and 1 1, right? So for if we have 4 number of locations, we need 2 address bits, right? So let's say this address bit as A and this address bit as B. Okay. Now, now what I'm going to do is I'm going to store the value 0 over here and I'm going to store triple 1 over in the respective locations. Okay. Now, if I want to access if I want to access this particular bit, what should be my address value? That is, what should be my value of A and what should be my value of B, such that I can access this particular location. If I want to access the data which I have circled, what should be the value of A and what should be the value of B? It's a straightforward question, simple question. A should be equal to 1, B should be equal to 0. If you are going to provide this particular address only, then you can able to access this particular data. Am I right or wrong? So if I'm going to give this particular RAM to you, and if I'm going to ask you, like take this data out from this RAM, okay, take this data out from this RAM at this particular location, then what you're going to do, you're going to provide this address as AB is equal to simply 10. Like let's say suppose if I'm asking you, if I have provided you this particular RAM, okay, and I'm asking you to provide, if I'm asking you to remove this data which is 0, which is present at the first location, then what is the address you are going to provide? You are going to provide AB is equal to 00. Am I right or wrong? Yes or no? Can you able to understand what I'm talking about? Okay, simple. I've given you a simple box. It may be RAM. It's a simple RAM. Okay, you don't know anything about RAM. Okay, you don't know anything about RAM. I have given you a simple box to you, and I've told you these are the addresses which are present, and these are the data items which are the present. Let's say, suppose if I want to take a data from there, you are going to provide that particular corresponding address so that you are going to retrieve or fetch that particular data from that particular location. Okay, now, if let's say if I'm going to retrieve a data from that particular last location, then you are going to provide that particular location and you are going to retrieve that particular data, right? Now, again, I'm going to repeat it one more time. Okay. So let's say if I want to implement a simple OR gate, then this is the truth table for that. And let's say if I've given you a simple RAM which is going to have 4 number of locations, and if I ask you to fetch a particular data from a particular location, you are going to provide that particular address, right? And you're going to fetch that particular data out from that particular location, right? Now, this is a simple concept which we are going to use for our LUT. that is nothing but LUT. This is the same concept which we are going to use it for LUT, right? Now, what are we going to do is, let me erase this particular slide. 1 minute. So we are going to have a two input LUT. So can anyone tell me, for a two input LUT, what are the number of locations which we are going to have? How many number of locations which we are going to have for a two input LUT? Exactly. A two input LUT is going to have exactly four number of locations, right? Now, how many inputs it is going to have? It is going to have two number of inputs A, and it is going to have inputs B, right? Now, this is going to have four number of locations like this. This is our LUT, which is going to have four number of locations, right? Let me draw it. Let me erase it one more time. 1 minute. So which we are going to have a simple LUT over here, which is going to have four number of locations because it is a two input LUT, right? And our inputs are A and B, okay? And this is our output Y, okay? Now, if you are programming this FPGA is going to contain this LUT, okay? This LUT is present inside a CLB. We are going to have a something known as CLB. CLB is nothing but configuration logic block. And what makes our FPGA configurable is the CLB. CLB is going to have inside something known as LUT. It is going to have other components also, but we are going to discuss about this LUT, right? Now, this LUT is nothing but it is going to act as your simple RAM example, which we have discussed right now, right? Now, if you are programming this FPGA, how to program that FPGA, what is the procedure, that and all other sessions we will discuss in future. Let's say if I am programming my FPGA, somehow this particular locations are filled with the values 0, 111. Sir, how it is happening, how we are programming a LUT, how we are configuring the CLB, that is all secondary. We need to understand the functionality of this LUT, right? Now, this LUT somehow we have programmed and the values of this LUT are filled with 0, 111, right? Now, as a user, let's say if you are having an FPGA board over here, and this is your output which you have connected to some LED like this, right? Now, and you have two push buttons over here like this. If you have two push buttons, and this push button you have connected with A, and this push button you have connected with B, right? Now you have something known as your FPGA over here. This FPGA will be connected to this LUT. This FPGA output is an LED, which is nothing but our Y, right? Now if you are providing A and B, let's say if your A is equal to 0 and B is equal to 1, now tell me which data, from which location the data will be retrieved and what will be the data. If I am providing the value of A is equal to 0 and B is equal to 1, from which location the data will be retrieved and what is the value of that particular data? Exactly. The value of the data that will be retrieved is 1, and the location from which it will be retrieved is the first location. Sorry, I mean the second location. Index is 1, right? So from here the data will be retrieved. Now, will LED will be turned on or it will be turned off? If our output is equal to 1, will the LED will be turned on or will the LED will be turned off? LED will be turned on, right? Now, let's say if you are going to provide A is equal to 0 and B is equal to 0. Let's say if I'm going to provide A is equal to 0 and B is equal to 0. Now, what will be the status of your LED? Whether it is turned on or whether it is turned off. What is the status of your FPGA? Whether it is obviously turned off, right? Now, if you don't know anything about LUT, if you don't know anything about FPGA, anything you don't know, you have a simple hardware in your hands, and if you're told that particular hardware or the FPGA is acting as an OR gate, what is that you're going to do? You're going to press A and you're going to press B. That is all the possible combinations you are going to check, and whether you are going to check with the LED. If you are going to provide A is equal to 0, B is equal to 0, you are going to check whether LED is glowing or not. Whether if you are pressing A is equal to 1 and B is equal to 0. Okay. I think someone will have this particular doubt also. If you want to provide A is equal to 1, then you are going to push the button. Push the button. Okay. And if you want to provide A is equal to 0, don't push the button. Okay. Like let's say, are you all aware of this button, right? Push button. Yes or no? Yeah. So if you want to provide the value of a is equal to 1, you are going to push the button, right? And if you don't want to provide the value of a as 1, then you are not going to push it. Okay. This is positive logic I'm talking about. Again, someone will ask about negative logic. That is again different story, and I don't want to complicate it, right? So I'm talking about positive logic, and if I'm going to press the button or push the button, my value of a is equal to 1, and if I'm not going to push the button, my value of a is equal to 0. Okay. Same with my value of b. So if I am told that this particular hardware is working as an OR gate, this is how I'm going to verify. But what exactly is going to happen internally? Are we drawing any OR gate logic, or are we drawing anything, or are we doing anything internally? No, we haven't done or we haven't drawn anything. Okay, we have just written our Verilog code. So what is going to happen? Excuse me. So what is going to happen? We have just written our Verilog code, right? So this code will be compiled and this code will be synthesized, and the synthesized gate level netlist will be converted into some file. I'm not going to discuss about that particular file, which is known as bit file, that we will discuss later. Okay. So this particular synthesized file will be converted into something known as LUT mapped logic. Okay. So the tool is going to take care of which LUT should be activated and what should be present inside that particular LUT. That and all it is going to take care, and it is going to configure this particular LUT such that if the user is providing this particular inputs, you are supposed to get that particular outputs. That's it. So is it clear for everyone how an FPGA is being configured and what is the logic of your LUT and how it is working? Is it clear? Simple. It's a simple static RAM we are going to have. It's a simple memory where all the possible values of that particular gate are present. If we are going to provide that particular values, it is going to work accordingly. It don't know what is what are we implementing, whether we're implementing AND gate or gate, it don't know. Just it has stored a set of values, and according to the addresses we are providing, it is providing the set of values. Let's say suppose if we want to implement this hardware is acting as an OR gate, right? Let's say if I want to implement this hardware, I want to configure this hardware to work as a half adder. If this hardware which I have, the FPGA which I have is working as an OR gate, right? I am going to configure it to work as a simple half adder, right? Now, what is going to happen? I'm going to have the LUT, and this LUT I'm going to take two input LUT only, because for a half adder we have only four. It's a two variable function, right? So what I'm going to do, I'm going to again have four memory locations. Now tell me what should be the values that should be present inside this memory locations. Anyone can tell me? What should be the values that should be present inside this memory locations such that this LUT can work as a sum, such that I can get the sum of a half adder. What should be the elements, or what should be the data items that should be present inside this particular LUT such that I can get a particular equation for sum? Exactly, 0 1 1 0. Why? Because sum is nothing but a bar b plus a b bar, right? A bar b plus a b bar is nothing but min terms m2, sorry, a bar b plus a b bar, exactly, m1 plus m2, right? That means in the second location you can have 1, and here also 1, and rest all is 0. Or else you can also refer to the truth table of your half adder, where we are going to have a and b 0 0 0 1 1 0 and 1 1, sum and carry 0 1 1 0. Is it clear for everyone? Yes or no? So this is how your LUT is going to be configured, and whatever the values you are going to provide as your inputs. Let's say if you're going to provide value of A is equal to 1, value of B is equal to 1. What will be the value of sum? Can anyone tell me by referring this LUT? If you're providing A is equal to 1 and B is equal to 1, and what will be the value of your sum? Exactly. Yeah, exactly. right? So carry is equal to 1, but we haven't drawn the LUT for our carry, right? Now, let's say, let's say 1 minute, you have written a Verilog code for you have written a Verilog code for your half adder, right? And this half adder code you have written assign sum is equal to A or with B. Okay. Compiler don't know whether you are writing half adder code, full adder code. Compiler don't know anything. It is just going to check for the syntax, right? And let's say it is syntax is everything is correct, then it will be compiled, it will be synthesized, and it will be converted into LUTs. Okay, so it will be mapped into LUT logic. Okay, how you're going to convert it into LUT and how you're going to program your FPGA, that is what we are going to learn in this particular sessions, right? Now it has been converted into LUT logic. Now in this particular LUT logic we are going to have A and B. Now in these four locations, what will be the data items that will be present? Can anyone tell me? What will be the data items that will be present in these four locations? Please see the code and answer. Exactly, 0311. The code, by mistakenly, I don't know how to write a half adder code, or I don't remember in my exam, I don't remember what is the code for a half adder. So, what I've done simply, I've written assign sum is equal to A or B. Okay. So, what compiler don't know anything. Compiler just going to check for the syntax and it is going to synthesize. The tool is going to synthesize and it is going to convert it into LUT based logic, right? Now, what it is going to do, it is going to fill these locations as 0 right? Now, let's say if user is going to give A is equal to 1 and B is equal to 1, what will be the output you are going to get? Can anyone tell me? Whether the output LED should glow or it should not glow. Yeah, in this particular case, it is going to glow and your output LED is going to glow. But whether it is functionally correct, you are intended to make a half adder, but is it functionally correct? No. So where is the mistake happened? So it happened in the coding level. Okay. So LUT mapping is correct and synthesizing is correct. Compilation is correct, right? It happened in the coding level, right? So what you have done? So instead of or, you are supposed to keep XOR, right? So this is how your code is being mapped into an LUT based logic, and this is how your FPG is going to be configured, right? So is it clear for everyone? Yes or no in the chat box, please? Now, my next question is, let's say if you are going to have a two input LUT with you, okay? If you are going to have a two input LUT with you, like let's say you are going to have a two input LUT. Now, can anyone tell me what are the possible number of Boolean functions you can form with this two input LUT? How many Boolean functions you can form using this 2 power LUT? Can anyone tell me? What are the possible Boolean functions you can form using this LUT? Okay. Are you all sure that you can only form four variable? Okay, let us write down. So what you have written A bar B bar, sorry, A bar B bar, A bar B, A B bar, and AB, right? So this is what you have written, right? Yeah. Okay. Let's say if I want to implement a Boolean function, simply A, then according to your definition, this should not be implemented. Am I right? So if I want to implement a Boolean function A using this two input LUT, that cannot be implemented because it is not present in this list. Am I right? If I want to implement a Boolean function A using this two input LUT, then it will not be implemented because you haven't listed in your list. Am I right? Yes or no? Yeah. So your list which you have written is missing some one more term which is known as a. Like let's say suppose if we want to implement a simple boolean function a, can we implement or not? So what type of logic gate is going to implement this boolean function a? Whatever the input which we are going to give, we are going to get our output. So what is that buffer? Like if we want to implement a buffer, we can get. Now, can we implement a boolean function which will just produce output b? Yes or no? Can we implement a boolean function which can implement this buffer simply b? Yes or no? Exactly, it can, right? So the formula, let me write down over here. Let me write it clearly. So if we have a two variable function, the total number of functions which we can implement is 2 power 2 power n. Okay. Here n is nothing but our number of variables. So 2 power 2 power 2, which is nothing but 16 possible Boolean functions which we can implement using a two input LUT. Okay. If we are going to have a two input variable, okay, or if we are going to have two variables, we can implement 16 functions. If I am going to have a two input LUT with me, then I can implement total 16 Boolean functions, right? So what are they? So I can implement simply function, I can get 0, okay, or else I can get f is equal to a dot b, okay, or else I can get f is equal to a dot b bar, okay, or else I can get f is equal to a bar dot b, okay, or else I can get simply f is equal to a, f is equal to b. F is nothing but my output, right? Now, or else if I can simply get a XOR with b, that is nothing but a bar b plus ab bar. This is also a function. And I can also get f is equal to a plus b, f is equal to a plus b whole bar, okay? And I can also get f is equal to b bar and f is equal to a bar, okay? And I can get f is equal to a bar plus b, okay, and I can also get f is equal to ab whole bar and f is equal to 1. So these are all the functions which I can implement. Total 16 number of functions I can implement if I'm going to have a simple two input LUT. See how many Boolean expressions I can implement. 16 number of Boolean expressions I can implement if I'm going to have a simple two input LUT. Assume if we are going to have a 5 input LUT with you, then total how many Boolean functions you can implement? Can anyone tell me? If we are going to have a 5 input LUT, which is not generally possible, if you are going to have a 5 input LUT, you can implement 2 power 32 Boolean functions, right? Okay. So generally, yeah. So it's a generalized formula for implementing the number of Boolean functions. You can refer Morris Manu for this. So it's a generalized formula that is 2 power 2 power n. Okay. Yeah. Function is nothing but, mm, I didn't get your point. Mm-hmm. Yeah. Okay, okay. So let me give you a brief idea. So let's say if I'm going to have a black box with me, and this black box is going to have two inputs. I don't know the functionality of this black box, right? So this is my output Y. Now, this output Y, it can be zero, right? Am I right or wrong? That means I'm not going to get any output. That is Y is equal to zero. Let's say suppose Y is equal to one. This is also a possibility, right? Now, my output can be A dot B. So these are nothing but my possibilities. If I'm going to have a two input black box with me, so there are total 16 number of possibilities which can be possible. Is it clear? So if I'm going to have a simple black box with me, my output can be zero, constant zero. or my output can be constant one, or else my output can be multiplication of both the inputs A dot B according to the circuit which is present. So these are the total 16 combinations which you can have using a two variable function. Apart from this 16 combinations, can you think of any other combination? No. So these are the all possible combinations if I'm going to have a two variable function. Okay. I think I have missed that particular thing. Yeah, thank you for adding that particular thing. It is, let me write down over here. A bar B bar plus AB. Okay. Anything I have missed here? And anyone want to add any other combination which we have missed here? Any other expression which we can form? Yeah. So is it clear for everyone? Yes or no? Please let me know in the chat box. And what about others? Is it clear? Yeah. Yes, exactly. Now, let's say if we are going to have three variable function or three input LUT, like how many combinations you are going to have? How many possible combinations you are going to have? 2 power 2 power 2. That is 2 power 8. So total 256, if I'm not wrong. 256, right? 2 power 8. Yeah. So total 256 possible Boolean functions you can implement, right? So this is how powerful a simple LUT is, right? So using a simple LUT, you can implement these many functionalities. Okay. So F is equal to A is a simple functionality. That is, whatever the input you're going to give, it is you're going to get an output. It's a functionality of this particular black box. If you are going to have multiply this is an AND gate. If you are going to give A dot B bar, it's a functionality. Okay, according to the requirement, you're going to design this particular thing, right? So maximum we are going to have four input LUTs and LUT optimization and how the tool is going to optimize this LUT and how the tool is going to choose LUT. That is all. It's an other subject which we can discuss later. But this is how your LUT is going to look like. That is what you are not going to write anything lookup tables in your code. You are just going to write down your Verilog code only. The tool is going to take care of how to choose an LUT, how the contents or how the data is being stored inside your LUT. The tool is going to take care of that. You are not going to worry about that particular thing. Your duty is no. That is not a bit file. Bit file is different. Bit file we will discuss in future. Okay. Bit file is different. Is it clear, ChatGPT? Yeah. So shall we move forward? Is it clear? Yes, no, please respond in the chat box. Shall we move forward? Sahil, I didn't get your text. LUT on load CLB. Yes. Okay. Now, and if you carefully observe this particular thing, in this particular diagram, they have written something known as programmable interconnects. That means you can also program this interconnect. Let's say, suppose if you are going to implement a complicated Boolean function, let me change the color. If you are going to implement a complicated Boolean function, right? Or if you're, yeah, LUT is in CLBs. Yes, exactly. Yeah. So if you want to implement a complicated Boolean function, which is going to have some, let's say, some 256 terms or something, right? So the tool is going to take care which CLB should be connected to which CLB and how the CLB should be connected to which CLB, and there will be so many factors like skew factor, clock jitter, routing, and there will be so many factors, right? So which particular CLB should be connected to which particular CLB to implement a particular function, that and all will be decided by the tool. And let's say suppose if we want to implement a function a bar b bar plus a b bar plus a b c like this, right? Now for implementing this particular function, the tool may select this CLB and this CLB and this CLB, right? So what it is going to do, it is going to connect these three CLBs for implementing this particular function. That means it is going to make this particular connection. Somehow it is going to make this connection, and we are not going to uh, in detail go and scratch our heads like how it is going to make our connection, right? So in our future we will see. Okay. So it is, if it wants to implement this particular function, it is going to program this particular interconnect. Let's say if we have reconfigured our FPGA, then it is going to remove this particular connection and it is going to establish these connections, right? And it is going to make the connections of these four CLBs for implementing our for implementing whatever the Boolean function we have. The tool will optimize and the tool will select which particular CLB should be selected and which CLB should be activated, right? So that and all also will be visible, and how many LUTs will be utilized in our code and how many LUTs are actually utilized and what are the LUTs utilized, that and all also we can see in our tool. Okay, that we will see later, right? Yeah. Any other queries? Uh, you're talking about this too? Yeah, it depends. The tool is going to decide, like it is going to calculate the latency, like it is going to take care of that particular things, right? So we are not yet started that particular thing. We haven't started how to calculate this latency and how to optimize this latency and how the tool is going to do that and how we are going to get the reports. We are not yet started that particular things, right? Yeah. Do we need to write all the possible functions in the code? No, 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 no. The possible functions why I've told that particular thing is I wanted to show you how powerful a simple LUT is. So using a two input LUT, you can get all this possible functionalities. You can get it, right? Yeah. Uh, yeah. Yes, Sohail. I think you have got my thing right. Right. Now, so the things which I've discussed till now was only for combinational circuits. So we have seen everything till now, which it was for a combinational circuit, right? Now, can anyone tell me quickly what is the difference between a combinational circuit and a sequential circuit? Yes, we have a memory, we have a feedback circuit. Sequential output depends upon exactly. Sequential circuit has a memory and it basically works with the clock, right? Now, so this CLBs don't, this LUTs don't have any clock or something. It is going to implement, and if we want to make our sequential circuit, we are going to include our flip flops also. Okay, so we are going to include our flip flop, and if we want to implement any sequential circuit, this will come into the picture, and this multiplexer is going to select whatever the output which we want from the LUT or the flip flop. Okay, so this is what our CLB is going to contain inside it, and it is going to implement whatever the Boolean function. It may be a combinational circuit or it is a sequential circuit, right? So this is how you're going to implement any Boolean functions, or and you're going to configure your CLBs, right? So this is what we have written. CLBs are basic building blocks, which is going to have lookup tables, flip-flops, multiplexers, and carry logic. Carry logic I haven't implemented because I don't want to make it so complicated right now. Okay, we will discuss step by step. So that is what we have discussed. Lookup tables for 4 input, we have total 16 memory locations, and for 6 input, we have 64 memory locations. Okay. So instead of building AND gates, OR gates, or XOR gates, FPGA stores something known as truth table of the logic function, right? So yeah, this is the definition of LUT. That is what we have discussed. And what is LUT? So the ASICs will have the gates at fabrication time, and FPGAs should be reconfigurable. So we are going to have something known as lookup table, which have the ability to implement any Boolean function, right? So this is what the examples I have included in the slides, which I will share you shortly. Yes. So that's about this particular session. So if you have any doubts or any other queries you wanted to discuss with me, you can stay and discuss, or else you can leave the session. I hope you have got some clear idea about what do you mean by LUTs and how FPGAs are basically configurable, reconfigurable this many times. What makes our FPGA reconfigurable this many times? Okay. Yes.